Hi, this is Steve Graves from the CSUN Geography Department and planetgeography.org. This video tutorial is going to show students a couple of statistical tricks and at least one logical trick in order to set up a chi-square test. So that's what we're going to do. What I have here is a list of cities in the San Fernando Valley with the number of students from each of those locations that attend the university that I teach at, and a distance matrix, or a list of distances between campus and each of these neighborhoods or cities. And the one that's taken out is Northridge, because there are so many students that live in Northridge but aren't really from Northridge that it doesn't make sense to leave it in there. It screws everything up. The idea is that we have the number of students and the distance, and according to the spatial interaction model, then we should be able to predict, based on the distance and the population of the city, a rough estimate about how many students should come from each city if we assume that each city is producing students at an average or a normal sort of clip. Everybody's contributing students to our campus in an even fashion. And so what we need to know is the population of each of these cities. And so rather than me just giving it to you, I thought I would show you the Vlookup tool. So I'm going to type up here in cell D1 Vlookup. And here's the formula. It goes Vlookup, and what this tool does is ask you, well, what are you looking up? And that's the lookup value, the first thing. And the thing that I'm looking up is the city of Arleta, or the word Arleta, comma, and then I have a table array that it's asking, well, where do you want to find Arleta? Oh, I want to find it in this table, and so I'm highlighting the whole table, and I'm pressing F4 to freeze that cell array, those sets of cells. So you notice the dollar signs and the cell references, another comma, and it says it's asking here column index number. It requires that Arleta be in the first column, so that's a given. But it's asking, well, what do you want to return from this column? And that's the column index number. And in this case, it's column 5. I have 1, 2, 3, 4, 5 columns. And in the 5th column is the population. So I'm going to enter 5, and I'm going to type in false because I don't want some town that is spelled similarly to Arleta. It'll do that. I want Arleta or nothing. Close parentheses and press enter, and there's the population for Arleta. It's in this table somewhere, and it's always good to check. So if I type in, I go to find and type in Arleta, it should appear somehow twice. And there it is. And there's the population, 34,370. And at this point I can copy this and paste it to the rest of the file. So the next thing I want to do is to copy this data, copy, and I'm going to put it in a new worksheet. And I'm going to just copy the values. This is population. And the next thing I'm going to do is I'm going to move these values over 1, and I'm going to put in here student 2, which is sort of, let's call that fake. And I'm just going to copy that over, so I have two rows of identical data. And here I'm going to enter a formula down below, and it's chi-square test. And that's going to give us a value, a p-value, that will indicate the probability that these two columns of data are the same. And it should be 1 because they are the same. So it's a 100% probability, basically, that they're the same. So the actual range, or this is the observed, is the B column, and the expected in this case is the fake number that we copied over, and that's in C. And if I close it, there's the 1. And all you have to do, which is cool, is go in here and change one of these values just a little bit. So let's make Woodland Hills, we'll drop it from 98 to 80 students. And you notice then this, now you're just a little less sure that these two samples are the same according to the chi-square test. And if we drop it to 70, now we're outside that 0.05 confidence level, because we're not 95% sure anymore. So let's just, you can just put that back up to 98, and that's our chi-square. All right, so what we're going to do next is to engage the formula for the spatial interaction model. And generally the spatial interaction model, I'll put it here, up here at the top, is equals population divided by distance. But normally that's also raised to some scaling factor, and this in your textbook doesn't talk about that, but that scaling factor is the friction of distance, and a lot of times it's just a 2 or a 1.5, and in this case I've calculated something out so that it's about 3.5, and that will give us data that is realistic. So this is the spatial interaction, and what this is going to do is going to provide us with an expected. So this is going to be our observed column in green, and then in this column that I will make this neutral color, this will be expected. So how do we do this? This is equals population divided by distance, and this is in miles. We're going to raise this to 3.5. And that tells us that we should have about 65 students from Arleta, and there are 71. So I'm going to copy this formula all the way down. If you're a student in my class, you could ask me how I got 3.5 as a scaling factor. Next, what we're going to do is engage the chi-square formula. And there it is. I just grabbed it off the internet. So chi-square is the sum of all of your rows of data where you go observed minus expected squared divided by expected. So this column will be observed minus expected, and we can do it in 2 columns if you want. Let's do observed minus expected squared. And then we're going to divide that by expected. So that'll be in this column. Widen it up a little bit. So here's observed, and that one is expected. So let's write this Let's see. This should work. Observed minus expected. Raise it to the power of 2. And then we need to add a second parentheses around that, just out of an abundance of caution. Always extra parentheses don't help, or do help. And then we want to divide that again by expected, which will give us a number. And the smaller the number, the closer the observed and expected are to each other. And now what I'm going to do is just press Control C and copy this all the way down to the rest of the column. So we have a bunch of outcomes, I suppose we should call them, and each of those is the sort of contribution to the chi-square. If we added them all up, the sum is 190, so this is chi-square, right? Equals sum, and that completes the chi-square test. Badly spelled. And then I can take this formula and perhaps copy it over here, and I just need to grab these boxes to make the observed and expected, put them in the right place, and that gives us the probability that those two columns of data are the same, and we can see that they're not the same. The way to get this goes straight to the p-value. To get p for this formula is chi-square distribution RT, right, and then it wants to know chi, the value there, which is our 190, and then the degrees of freedom, which is, in this instance, the number of observations we have, which is 21 neighborhoods minus 1. So that's 20. Boom. And it gives us that tiny number. This is being rendered in scientific notation. So if we want to change that, we have to click on number, and it's again 0, and we can click on this, and this is quite certain, our probability that these columns of data are different. What is interesting here is the contribution. So we want to know what is that number as a percentage of the overall. So I'm dividing my sort of contribution by the total amount to get a percentage. So that, 71 and 65 observed and expected, those are close, and that's less than 1% of the chi-square contribution. What we find is that there are certain places like San Fernando and then Silmar, which are producing, in this case, too many students. Same for, for San Fernando, that it has 57 students but should have fewer, according to this. And then some of the other places, Canoga Park, 111 students and should have 117. So that is the chi-square test.